Hi again. In the previous session, we continued the evaluating and valuating insurance products, and we looked at continuous case. Now we will move, similar to what we developed, we will move to the discrete case. And what we mean by discrete case, that payment, like insurance benefit payment, will be made at the not at time of death, but rather at the end of the year of death. So the idea here is you have an insured person, age X, and the insured person, age X, survived to X plus K, and then the death happens within the this year, the kth year, so between K and K plus 1. So the age will be X plus K and X plus K plus 1. Death occurs here. In the previous continuous model, what we did, we just used like the fact that payment will be made at the moment of death, and we find the actuarially present value. But for us here, even death happens here, we will wait until the year here to make the dollar value. And then the dollar value will take it here, the actuarial present value. Right? So it's the same logic, but the death occurs at the end of the year. Let's look at how we can calculate the actuarial present value. It's the expected value of the present value. But what's the present value of this one? It's the expected value of, now for an individual, for if the death occurs in the between K and K plus 1, then the present value of it is, you have V, you discount it to K plus 1. And how we will calculate the expected value? As always, expected value, multiply it by the probability of this event to occur. So then VK plus 1, right, because we discount from here, right? We bring it from K plus 1. Then we need to multiply it by the probability. What's the probability to get the expected value? What's the probability of surviving? You need to be careful here. The probability to survive here and die here. So we need to multiply it with the probability of survive to from X to X plus K. So multiplied by K P X. So probability to survive to year K. And then death occurs in the next year, right? Then we multiply death is VQ, and then this will be death here. So we have X plus K. As always, there is one, you can put one here, or you don't need to put one. It's understood, right? So again, like the idea here is survive to age X plus K. Now die in age X, or not between ages X plus K and X plus K plus 1, right? Because this is the death. So the probability, this is the probability of surviving to here, and death occurs here. But this is, if we know, K, if K is known, right? But if it's not, then you do it for every single year. So if you want, this is for, if you want for every single year, and you want to discount, then similar to what we did in actuarial, like the value of the insurance, whole life insurance, we start with the whole life insurance. Recall in the continuous case what we use, if you remember, AX, and we use bar. But now for benefit paid at the end of the year, paid end of the year, end of year of death. So we remove the bar. So if the bar is the paid at the moment of death, we remove the bar. And the other point, if you remember the same logic, if you remember what we did in the continuous case, we take the integration, but in discrete case, in continuous case, we take integration. In discrete case, we sum, and we sum exactly this term, each one, the vk plus 1, and multiply it with the probability. So we sum vk plus 1, we multiply it by probability to for a life age x to survive to age k and then die in the next year, right? And this is very important, right? I usually don't really memorize this one because I do the math quickly. We'll take a few examples, but it's good to know how, you know, we sum it for all terms. And here we start from k equals 0, and this because it's until, you know, death, until infinity, right? And this is the whole life insurance. And we did other models, if you remember, not only whole life insurance, we did other models in continuous case. Let's look at term insurance. Or before do the term insurance, what if you wanted to do the second moment? Second moment, simple. Same thing, k equals 0, infinity. Now, second moment, the benefit will be raised to 2. So v, now you raise everything to 2, multiply k plus 1, right? So that's where you get the second moment multiplied by, the probability does not change, right? px qx plus k. Right? This is for the second moment, right? So this is the second moment, and this is the first moment, right? This is the expected value, and this is the second moment, right? And same logic what we did in continuous case, we can do them now very quickly because the same logic. ax, what if you have something like this? In this continuous case, we know it. We did questions like this. We took the formula. Now the discrete case, the same thing. Death occurs. This is term insurance. And discrete case. Same logic, right? So we take summation, same logic, v, k plus 1, and then multiply by k px, q, x plus k. And if you visualize it here, this is x. So we start from k equals 0. So k equals 0 here, then x plus 1. So k will be 1, and up to n here, and up to here. So dollar paid at the end, if death occurs here, dollar paid here, right? And this is where we need to be careful here, because n here, if you have n here, if we continue n, then you will have k plus 1, you will have a benefit paid here. So this upper term should be n minus 1. So n minus 1 here. So if you plug in n minus 1 here instead of k, it will be then n, right? If you try to plug in n minus k here, n minus 1 k plus 1, it will be n. So that's why we need to the last term n minus 1. But later on when we do calculation, we see it. We see what I mean. And the one on top of x to say is term insurance. Same logic here, we can have ax without the 1. Oh, sorry, here n I meant. Yeah, n. If it's without the 1 on x, so there is no 1 on x, and this is what we call the endowment insurance, and this one can be the term insurance plus the pure endowment. And what the pure endowment is the same one because it's discrete. And even when we talked about this one in the continuous case, it's discrete. It's the same one. Nothing gets changed here, right? So we have this formula as well. Now, what if you wanted to have a deferred annuity, a deferred insurance? Deferred insurance, you have x, you want to defer it up to x plus n, for instance. So you want the insurance to start here. So this one, we did it in the continuous cases. If you remember the continuous case, it will be very easy. You have n, little bar, and then A for the insurance, X, without bar here. We don't need the bar. So it's deferred for n period, right? And this is in discrete case, you can do it in multiple ways. You can sum from here. Now we need to sum from n, k equals n, to all the way to the end, and then v, same logic, v k plus 1, then you have n, k, I mean k px, then you have qx plus k, and this is the, so you start from here and then you keep going, same logic. The only thing that difference here that you start from this one. So basically you start from here and you started discounting back to here, right? And what we can also recognize that NAX is equal, you can think about it also if you have AX plus N here, right? So if you are here, now this one, how you bring it back? We bring it back with the actuarial discounting factor, NEX, right? So you bring it back. So if you are here X, you have X plus N, you have AX, and you have AX plus N. So if you want this one to bring it here, then it become NEX AX plus N. And why? Oh, sorry, let me fix it here. And why this is the discounting factor? And what we mean by discounting factor is not the interest theory, this is the actuarial discounting factor. Right? So yeah, I mean, this is maybe a little bit of definition. Let's take example, but again, you have so many formulas, so many notations, but if there is logic, the only thing different than the previous time that we removed this bar. So everything is the same, we only removed the bar. So everything else stays the same. Let's take one example. Let's see what I mean. Like take one example here. See how we can compute it. Okay, so I have made this example life table below is a life table for a cohort, a cohort of maybe 1000. So we have 1000 lives, and we already have the life table for this 1000 life. And it happens that we have them at age 90, 91, 92, 93, 94. So 4 years. And then in life table we have LX. Remember LX, like the cohort. We start with 1000, then the 1000 they become 800, then like 200 passed away, 500, then 100. By 94 all of them died. So since we're starting from X90, what you can do, you can add another column to this one to help us. Let's call it K. 0, 1, 2, 3, 4. Right? I add another column called K. Let's say that interest rate is given to us by I interest is 0.5%. Right? It's given the question. We have a few questions to answer here. We are asked to find, maybe let's say find A90. So we are asked to find A90. Okay. So how we find A90? I usually prefer to have the timeline. It helps me to understand, to visualize things. So 90, 91, 92, 93, 94. You might consider this one as, you know, if you want, you can remove the 90 and write 0, 1, 2, 3, 4, like the K. So we start with a cohort of 1000, and then it become 800, then it become 500, and 100, and 0. So obviously there is death. So we need to find A90. And we don't see any bar, so it's okay, it's discrete. So the payment here, or here, or here, or here, it depends on death. So now this one, remember the formula, I said we start from k equals 0 to n to infinity, which is here up to 94. And then what we need to do is to have vk plus 1, then a life age x, survive to year k, then die in the next year. And this formula, I usually don't use it when a question like this. I just solve it immediately, but just good to remind you the formula. If we want to solve it immediately, now we start year by year. So the first year between 90 and 91, so between K0, K1. If death occurs here, benefit is paid at the end of the year here, right? So benefit is paid here, so we need to discount it. How we discount it? It's V, right? But we need the probability of death occurs here, and this is Q90, right? Plus, now let's take the second case. Now let's say death occurs here between 91 and 92. So if death occurs here, then the payment will be made here. So V raised to 2. But what's the probability for death, you know, to survive to 91 and die here? Then this one is, we have P90, then multiplied by 90, and then death occurs here, then Q. What's the probability for somebody here to die here, like already survived to 91? It's a Q91, right? And then we keep doing this, right? Now we add to it plus. Now let's say the death occurs here. If death occurs here, the dollar payment will be made here. Now to bring it back here, we need V to 3. You know, the discounted value, V3. And then we need the individual to survive to here. The individual to survive to here, so it's somebody P90 to survive 2 years and then die in the next year, so Q92, right? If we keep adding now the term, maybe I should just. Now the last term we wanted is, now the death occurs, let's say here. If death occurs here, the dollar amount will be paid here. So we have V, it should be to 4. And then the individual needs to survive to the beginning of year 93. So for somebody 90, you need to survive 3 years and then die in the year 93, between 93 and 94, so the individual will be 93, right? So this should be it, right? So now let's implement it, and let's keep V as is. V, what's Q90? Q90, we go back to the line here. A Q90 is somebody like death occurs here. So we have 200 deaths divided by 1000 plus V2. Now what is the probability for somebody to survive to age 90? Probability P90, P subscript 90. So for an individual to survive to age 90, from age 90 to 91, I mean here, because 1 year is here, then to survive is 800 divided by 1000, right? And then death occurs this year. How death occurs this year? For the cohort, we started at 800 and we lost 800 minus 500, so 300 death, right? V3. Now somebody at age 90 survived 2 years, so the cohort we have 500 survived to over 1000, 500 over 1000, and now the death occurs between 92 and 93. So we have another 92, 93. We have 500 minus 100 is 400 divided by, we started here, 500. Now the last one is V4, and we know it's V again. It's the 3P9, smaller V maybe. 3P9, so somebody age 90 survived to 93. So we have how many survived to 93 is 100 over the cohort of 1000. And multiplied by Q, sorry, this should be 93. Why is that? Q93 die in the next year. So how many deaths occurs here? All of them. It's 100 over 100. The cohort of 100 pass away. Right? Now there is lots of cancellation here, but what you see, we can summarize it to 0.2V plus, now this cancel out with this, 0.3V2 plus 0.4V to 3 plus, now this is a why I have here 100, not 1000. Now they cancel out this one with this one. We have 0.1V4. If you have whole life insurance, these terms should add up to, for this kind of case, should add up to 1. I'll come back to it in a second. This is because now this is a distribution, right? Why they add up to 1, I'll quickly go back. Let's go back to this formula. I wrote this formula this way, right? I wrote it this way to help us to understand it. This one can be, if you think about it, can be written K plus 1, VK plus 1. And this can be now somebody, we have K, Q, X, the deferred mortality. We did it before, I didn't want to complicate it again. This is the deferred mortality. And the deferred mortality, if you do it for everyone, it's a distribution. It's a valid distribution. It will add up to 100%, right? It's not complicated, but just in case, you know, we wondered why they add up to 1. Now you can use your calculator. We have interest. We said it's, if you remember, we said interest is 5%. So you can do that quickly. So I'll do it in my calculator quickly. So we have 0.2 multiplied by 1.5%. Did I do 5%, right? Yeah. Plus 0.3 multiplied, I do it all at once, 0.5 raised to -2, plus I have 0.4 multiplied by 105 raised to -3, plus we have the last one, 1.1 multiplied by 1.05 raised to -5. I got 8, 9. I need to double check it one more time. I think I made a mistake. 2, 3, 4, 1. Can I just do it one time quickly? Make sure I'm using this correct interest. So all of us. You can also take your time to calculate it. For this equation, interest is 5%. Okay, let's do it one more time. So one more time is 0.2 multiplied by 1.5 raised to minus 1 plus 0.3 multiplied by 1.5 raised to minus 2 plus 0.4 multiplied by 3 plus point. I think I figured out I made a mistake. Raised to Yep, correct. Very good, correct. And you should verify it yourself. Now, what if you want to do, the question asks you to find 2ax. This is the second moment. Second moment, it's everything is the same. If you remember the formula, it's you have everything is the same. Like everything you have here is the same. The only thing is vt k plus 1, right? And you multiply it by everything. The probability is the same, right? kpx and qx plus k. So everything is the same. The only thing, the v will raise it to 2. So to do it quickly, this one, all you need to do, you take this line and you just the v raise it to 2. It will be 0.2 v2 plus 0.3 v4 plus 0.4 v6 plus 0.1 v8. And this should be easy. I mean, you can do it quickly. I don't want to calculate it for you, just to tell you that it's done easily. Right. Now let's take another question here. Let's take, for somebody age 90 wanted a term insurance only for 2 years. And this term insurance is 1 on top of it. 1, it tells us it's term insurance only for 2 years. Same logic, you do it only for 2 years. If you go back to this line, you don't need to do it everywhere. You do it for this period here. So you do it for 2 terms. So it's exactly the same thing, but you do it for 2 terms, which you don't need to do it again. All you need to do is to do 0.2v plus 0.3v2, the first 2 terms. But if you want to do it again, you do this one. Oh, sorry. If you do it to the first 2 terms, you get this one. Right, and then if you calculate this one, it will be, I did it, 0.4626. What if the question, we need to be careful in actuarial science, the notation is very important. For 2 years, but we don't see 1 here, we remove the 1. Simple. This is the endowment, the endowment insurance is the term insurance for 2, and you add to it the A90 2 and the 1 on top of the 2, on top of the angle, right? So this one we already computed it to be 0.4626. This one can be done easily. What is this? This is the discounting factor. How we discount in actuarial science is you need to survive as well as you need to discount. So discounting for 2 years, it's easy, V2, but surviving 2 years for somebody 90, it's the same, P90, survive 2 years, right? It's so easy. Now this one can be written 0.4626 plus V2. What is 2P90? Surviving 2 years. Let's go back to our line. So somebody is here to survive to here. To survive here, we have 1000, we ended up with 500. So once they ended up, the cohort that survived is 500 over 1000, which is 0.5, right? And this is easy. If you do it, it will be 0.916, right? You multiply V2 using interest of 5%, right? So now let's also find another one, 2A90. No, we did the 2, where we will defer it for 2 years. So this deferred annuity for 2 years. Deferred annuity for 2 years, you can do it in multiple ways. One way is, well, let's do it in the easy way. The easy way is that you take A92 and then multiply it by 2E90. Not the easy way, but one way. And the other way is, yeah, I mean, you can do this one because we have the 2E90, which is already here. This one is also, you can write it also TE90. You already calculated, or actually I didn't compute it, but we can compute it quickly. V2.5. This is it. Now A92. A92, I mean, there are several ways how to compute it, but let's do it just we can quickly compute it on this line here. So now let's compute on this line. Yeah, it's getting crowded, but we wanted to calculate here A92. Now we are here. We wanted to compute A92. What's A92? We are here, we're not at 90, so we started with 500. So if death occurs in the first year, we will have V, because we are coming back to 92, we're not going back to 90. We have V, and how many deaths happen? We started with 500, we ended 100. So there are 400 deaths over what we started, 500. Plus, now we survived to here. So, well, now if death happens here, the dollar here will need to get it back to this period here. It will be V2, right? Because we're getting it back to here. Now we're evaluating at this point, right? And then we need to survive from 92 to 93. So the opposite of this one, survival will be 100 over 500. Multiplied by death happens here. So we have start 100 and all of them die. Yeah. So it will be 0.8 V plus, now will be 0.1 V2. Eight. I got 0.8526. Okay, I got it to be this number, right? So let's get this one back. Here. Still have it in my calculator. So all I need to do is to type it in. Multiplied by 0.5, enter, multiplied by 0.5 raised to I got to be 0.4278. I'm reading from my note just to double check what I did. It should be okay. It should be okay, but can I double check this one? I don't want to give you a mistake here. You have, it's always good to double check. We have 400 death over 500 with V, then we have survived 100, and then all of them, they died. So 1 over, I made a mistake here. Because we have 100 over 500. Yeah, I made a mistake. So let me do it again. 0.8 multiply by 1.05 plus 0.2 multiplied by 1.5. Let's see if this is, yeah, correct this one. Sorry for that. Today I'm making so many mistakes. So the problem here, I calculated this, it's 100 over 500 is 20%, right? Correct that, please. Yeah, sorry for this mistake. Yeah, did so many mistakes here. But the answer, the final answer, I copied it from my note. It should be okay now, but I'll double check it one more time. Yeah, good. Yep. Yeah, correct. But yeah, if we make a mistake, it's always, there is a way to verify. Let's verify. And remember what I said, A90 should be equal to A90 to 2 plus 2A90, right? They should be equal. This is a relationship that it should be clear. If we evaluating everything here, so you have the A90 here, and you have, it should be equal to here A92, but because you bring it back here, it becomes 2A90, right? And now you add to it this one for this period, A92. So now if you add this one to this one, it should give you this one, right? It's simple, right? This is the we took a few examples on it. We took the formula in under continuous, and we now under discrete also we took it. Let's verify, see if we got it right or not. We calculated the A90 to be 8904. 8904. So let's see, we calculated the term insurance, not this one, the one with 1, 4626, and we computed also this one, the one I made mistake with, is 4278. Now let's verify. It's good that I have them saved on my calculator. 4, 6, let's just double check because my calculator I have different number. Four, 6, 2, 6. Why I don't have 4, 6, 2, 6? Yeah, I didn't calculate that one. Yeah, but that's good. So if you add these two guys, they add you, yes, correct. 1, 4, 6, 2, 6. Yeah, 8904. Very good. So this is correct, right? So this is another formula, of course, like we took it before. So if you have the AX should be equal to AX plus N AX plus, oh sorry, the deferred one, right? So the deferred one plus that one, and this one can be written also AX and EX ax plus 2 plus n. Those formulas are very, very important. Very, very important. Now, so we already started this like this recursive relationship here. We already started it. But what if you have the n is 1 year? And many times, you know, you have a question with 1 year in, probably I'll bring one in exam. So if it's, yeah, I mean, it can be any term. The n can be any term. But if you have ax, you have x here, and you have x plus 1. Many times you have ax, maybe 2 years, 1 year, but sometimes I'll just want 2 years, not more than this, so to challenge you. And you want here ax plus 1. X. The relationship between these guys, so you have ax, so if death happens here, there is $1 here, so v, but death happens in qx, and then if death does not happen here, then you can get the ax plus 1. Ax plus 1. How we bring this back? Actuarial present value, nex, but you don't have the n, we replace it with 1, so it's actually surviving px, right? Survive 1 year, and you bring it back with v, right? So this is a very good actuarial notation. We need to keep it in our mind. Same logic with 2ax also, you can write it the same logic, but because we have the second moment, all the v's needs to be raised to 2. You know, these are, you know, a straightforward application of this one, right? But you can extend it to the n more than 1. Let's take one example here, just to finish this session on this one. This is quite interesting little example to help us to see how we can do multiple steps. Now you are given a 60 to be 0.585, and you're given also a 61 to be 0.605. Oh, so a 61, yes, 605, and you are given also further information that I equal 5%, and what's interesting here, the mortality in year 60 is the same as mortality in 61, you know, so those are given. The question here is to find a 62. Very interesting. So obviously we need to find the Q, the mortality, because mortality gives us also the probability of probability of survival. So let's draw a line here. Always good to draw a line. So somebody is age 60, 61, 62, right? So let's start with A60 and A61. How we can relate these two things? We need to discount this back, right? So we have A60. We can now remember what I said. A60 now, death happens in this year. If death happens in this year, then you have VQ60. But if death does not happen this year, then you will survive to 61. So V, and you discount it, surviving to 61, P60, sorry, survive to 61. So from 60 to 61 is the opposite of dying, Q60. We take P60 and A61, right? Let's put in what we have. What we have is A60 0585, 0585. Let's factor out the V. What we have is Q60. We don't know what it is. And we talk of the V. But now P60 is 1 minus Q60. What is A61? Let's look at A61, 605. Now the V, we can take it here, so it becomes 1 plus I. So now we have 0.585. Now multiply it by the reciprocal of V, which is 1 plus the interest, which is 5%, multiplied by 105. So we have 0.61425 equal. Now let's simplify it here. This 605 multiplied by 1, it will be 0.605. Now this one, 605 multiplied by q, but in negative, and you add to it 1, it will become 1 minus this one, right? So 1 minus 0.605, it will be 0.395 q60. Right? Take this one to the other side. Plus, you will get 1.2925 equal 0.395 q60, then q60, then divided by, this one is mistake, you know. And this is how you verify. I got q to be greater than 1. It's impossible. You cannot get the q greater than 1, and this is how we verify. So I made a mistake. Apparently I add them up. I should have not, of course, added them up. This should be negative sign, right? I made a mistake here, so let's correct it. Minus 0.605, right? It's very important for you to verify your answer by making sure that the probability cannot be exceeding 1, right? If you, in the exam, you make this mistake, right away you figure it out. The probability cannot be exceeding 1. Now this one divided by, and now it makes sense. The probability is 0, 2, 3, 4, 2. Right, so it has to be less than 1. You cannot have a probability of death greater than 1. And the beauty of this, the question tells us that Q are equals. Q60 is equal to Q61. So this one is also equal to Q61 for this special case. Now let's do A61, the same thing as we did with A60. And A61, 61, 62. So if death happens here, you have probability V multiplied by a probability of death, which is Q60. Let me I kept my Q60 in my calculator so I can come back to it. Now, if death does not happen here, then you will survive is P60, which is 1 minus this one, right? Yeah, I mean, it should write it correctly 61, but because in this case they are equal, it doesn't matter if you write it 60 or 61, right? And then A62. This one is given to us, right? Let's make sure what is A61 is given to us to be 605. Well, the same thing what I did is multiply by 1.5 the reciprocal of interest, so I can get rid of this. Q61, we have it here, plus 1 minus Q61, which we have it here, A62. You can do it all at once now. Let's do it all at once. We have 0.605 multiplied by the reciprocal of V, which is interest, right? Then we subtract from it the Q61, then you divide it by 1 minus Q61, and what I got here is A62 A62 is 0.627. All right, so we finish this. Now we'll next session we'll try to look at increasing, decreasing, certain insurance that not one single value but multiple values. All right, take care.